Welcome dear learners. We are continuing the course Quantum Chemistry. In the present module, we are discussing angular momentum operators. In this module, the contents are angular momentum operators in Cartesian coordinates, spherical polar coordinates, angular momentum operators in spherical polar coordinates, commuting properties of angular momentum operators, and properties of Hermitian operators with proof. First of all, angular momentum. It should be noted that the momentum of a body which execute rotational motion is termed as the angular momentum capital L. The angular momentum is a vector quantity. The angular momentum vector L is equal to I vector multiplied with omega vector. That is, the property of any rotating object given by moment of inertia times angular velocity is the angular momentum. That is, angular momentum vector is obtained by multiplying moment of inertia vector with the angular velocity vector, or simply L is equal to I omega. Hence, on a consolidation, angular momentum is the momentum of a body that executes rotational motion. Components of angular momentum. The angular momentum capital L can have three components, namely Lx, Ly and Lz. These three components represent angular momentum along the Cartesian axis x, y and z respectively. And Lx is given by the expression Lx is equal to y into pz minus z into py. Ly is equal to z into px minus x into pz. And last, Lz equal to x into py minus y into px. Here, px, py and pz are linear momentum components along x, y and z direction. There is an easy way to represent this expression. To remind this expression, there are some simple methods. I will show you that method. Let x, y and z are three Cartesian coordinates. First of all, we are going to write expression of Lx. That is, among three coordinates x, y and z, x is already mentioned here. Then take the next, that is y. Y into angular momentum of other component, that is Pz. Then its opposite, minus z into angular momentum of y. Now we can take the second angular momentum component, that is Ly. Y is here. Then go in a circular fashion. Then after y, z is there. So z into next component is x. So z into px minus the opposite, x into pz. That is the value of Ly. And finally, it is possible to represent Lz as z is here, then x. X into py minus y into px. These are the three expressions for components of angular momentum. The component of total angular momentum are related to the total angular momentum by the relation L square equal to Lx square plus Ly square plus Lz square. This is the relation connecting total angular momentum and its components. Now, angular momentum operators. It should be noted that angular momentum is a physical quantity. In quantum mechanics, there is operator corresponding to angular momentum. That is, to a very observable in classical mechanics, to every physical quantities in classical mechanics, there will be linear Hermitian operators. So, it is possible to derive angular momentum operators corresponds to each and every component of angular momentum. We have three components of angular momentum, namely Lx, Ly and Z, Lz. We already learned about the three components. Now it is possible to derive the component operators using operator postulate. So, as per the operator postulate, it is noted that we can create operator corresponding to an observable. First of all, we have to write the classical mechanical equation, then replace the terms Px, Py and Pz respectively by minus IH cross dou by dou x, minus IH cross dou by dou y and minus IH cross dou by dou z. After a rearrangement, we will get operators corresponding to the observable. So, here we are going to derive the operator corresponding to Lx. That means we are going to derive an operator corresponding to x component of angular momentum. That means we have to derive expression for Lx hat. For this, we are having the classical expression Lx is equal to y into Pz minus z into Py. As per the operator postulate, to get to the operator, we have to replace Px, Py and Pz by minus IH cross dou by dou x, dou by dou y and dou by dou z respectively. So, this term Pz should be replaced with minus IH cross dou by dou z. And Py should be replaced with minus IH cross dou by dou y. Therefore, Lx hat is equal to y into minus IH cross dou by dou z minus z into minus IH cross dou by dou y. On rearranging, if I can take IH cross outside, then I will get the expression y into dou by dou z minus z into dou by dou y. This is the expression for Lx hat. This is the expression for Lx hat. Similarly, it is also possible to derive expression for Ly hat and Lz hat. We can proceed in the same way. First of all, we have to write expression for Ly hat. And to write the expression, there is an easy method. We can proceed like this. X, Y, Z. Lx is already here. So, y into Pz minus z into Py will be the expression for Lx. So, we are now going to write the expression for Ly. Then only we can move on to its operator. So, Ly equal to z into Px minus x into Pz. So, to get the operator Ly hat, we have to replace Px and Pz by minus IH cross terms. That is z into minus IH cross dou by dou x minus x into minus IH cross dou by dou z. As proceeded in the previous way, minus IH cross can be taken outside the bracket and we are getting z into dou by dou x minus x into dou by dou z. This is Ly hat. Similarly, we can also derive expression for Lz hat. For that, we require Lz first. Lz is equal to x into Py minus y into Px. To get Lz hat, we have to do the substitution. That is x into minus IH cross dou by dou y minus y into minus IH cross dou by dou x. Taking minus IH cross as common, minus IH cross into x into dou by dou y minus y into dou by dou x. This is angular momentum operator corresponds to the z direction. Thus we have derived three component angular momentum operators by using the operator postulate. Now this is the consolidation of the result. Lx is equal to minus IH cross y into dou by dou z minus z into dou by dou y. Ly hat is equal to minus IH cross z into dou by dou x minus x into dou by dou z. And finally, Lz hat is equal to minus Is cross x into dou by dou y minus y into dou by dou x. These component operators are related to total angular momentum operator. Square of the total angular momentum operator by the relation L square hat is equal to Lx square hat plus Ly square hat plus Lz square hat. That all about the angular momentum operators. Now we are moving to a new coordinate system that is called spherical polar coordinate system. We are introducing spherical polar coordinate system to cite about angular momentum postulate in a spherical polar coordinate. What we learned is angular momentum operators in Cartesian coordinate. Now we are trying to change the coordinate into spherical polar coordinate system. In a spherical polar coordinate system, there are three variables, namely one r variable, theta variable, and phi variable. Among these three variables, r is a distance part, theta and phi are two angle parts. Thus, Cartesian coordinates has three variables x, y, and z. But in spherical polar coordinates, there are three variables r, theta, and phi. And now we are going to study what these three variables designate. What are these three variables in spherical polar coordinates? So, we can represent the spherical polar coordinate system by starting from a Cartesian coordinate. And I am pictorially representing that. Let this be the origin. This represents the y-axis. This represents the z-axis, and this represents the x-axis. We can take any direction because three coordinate axes are mutually perpendicular to each other. Now this plane is simply the xy plane. Now let us consider a point P in space. This is a point P in space. This is marked as P of x, y, z. Since its position is represented by three Cartesian coordinates x, y, and z. The distance from origin to the point P, the distance from the origin to the point P, that distance is taken as r. That is the first variable in spherical polar coordinate. This line r or OP makes an angle theta with z-axis. That is, theta is the angle between the line R or OP with z-axis, and the angle theta is here. So we mentioned about R and theta. Now one more variable is there. That variable is also an angle, and that is called the phi variable. In order to get to the phi variable, we have to move a little more. That is, we have to take a projection of P on the xy plane. Let the shadow of P fall in xy plane, and that point is marked as Q. That point is marked as Q. Or Q is simply the projection of the point P in the xy plane. Now I am connecting the line PQ. It should be noted that the line PQ is parallel with the z-axis. Now we can construct a plane containing the line PQ and the z-axis. The line PQ and the z-axis. This is the imaginary plane that contains line PQ and the z-axis. So here there is a plane containing, one side is z-axis, other side of the plane is the line PQ. P is the point and Q is the projection of the point P in xy plane. this plane containing z-axis and the line PQ makes an angle phi with x-axis, that is phi. So this is angle phi, this is angle theta, and the distance is r. So there are three variables in spherical polar coordinate system, namely r, theta and phi. These three spherical polar coordinate variables related to Cartesian coordinate by the expression x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. This about the conversion factor between Cartesian coordinate and spherical polar coordinate. Now we can have angular momentum Lx, Ly and Lz, also total angular momentum, to be expressed in spherical polar coordinates. This about the expressions that gives Lx hat, Ly hat and Lz hat, also total angular momentum operator in spherical polar coordinate. First of all, Lx hat is equal to minus IH cross sin phi dou by dou theta plus cot theta cos phi dou by dou phi. Ly hat is equal to IH cross minus cos phi dou by dou theta plus cot theta sin phi dou by dou phi. And finally Lz hat is equal to minus Is cross dou by dou phi. The total angular momentum operator L hat is equal to minus Is cross phi hat dou by dou theta minus theta hat sin theta into dou by dou phi. This about the conversion between spherical polar coordinate and Cartesian coordinate with respect to angular momentum operators. So these are components and total angular momentum operators in spherical polar coordinates. Now we are discussing a very important area, that is nothing but the commuting property of angular momentum operators. If two operators commute, definitely the commutator will be equal to 0. It should be noted that the total angular momentum square and any one component of angular momentum Lx, Ly or Lz, the total angular momentum square and any one component angular momentum can be simultaneously and precisely determined. We learned that there is connection between non-commuting property of operators and uncertainty principle. If two operators corresponding to two properties will not commute each other, their measurement is not possible simultaneously and precisely. For instance, the position operator and momentum operator will not commute each other. That implies the properties position and momentum cannot be determined simultaneously and precisely. Here, the square of the total angular momentum and any one component of angular momentum can be simultaneously and precisely determined. That means the commutator corresponds to L square and any one component operator of angular momentum have 0 value. That means I can write L square hat Lx hat equal to 0, L square hat Ly hat equal to 0, L square hat Lz hat equal to 0. That means their commutator is equal to 0. Commutator is equal to 0 means the properties can be simultaneously and precisely determined. What is the meaning of this? L square hat Lx hat commutator is equal to 0. What is the implication? The implication is that square of the angular momentum operator and component operator along x direction are commuting each other. That means the properties square of the total angular momentum and component along x direction can be simultaneously and precisely determined. Moreover, moving on to these three components, it should be noted that it is impossible to determine any two components of angular momenta simultaneously and precisely. That means Lx hat, Ly hat will not commute each other. Ly hat, Lz hat will not commute each other. Lz hat, Lx hat, I am representing it in a cyclic fashion. X, Y, Z, Zx like that, not equal to 0. The implication is that the component, the commutator corresponds to any two component operators of angular momenta is not equal to 0. That is, the properties represented by them cannot be determined simultaneously and precisely. That means it is impossible to measure any two components of angular momenta simultaneously and precisely. It is more appropriate to find out the exact value of this commutator. It is possible to find it out by using the commutator relationship, and on applying suitable simplification procedure, we will get the values of these three commutators. And the value is again can be easily studied. X and Y are here. The commutator Lx hat, Ly hat is equal to, one component is missing, that is IH cross into Lz hat is the value of the commutator. Now I am taking Ly hat, Lz hat. Okay, here one component is missing, that is Lx hat. So the result is IH cross Lx hat. And for the last case, Lz hat, Lx hat is equal to, one component is missing, that is Ly hat. So result is IH cross Ly hat. IH cross Ly hat. If somebody is asking about Lx hat, Lz hat, we have to put a minus sign here, minus IH cross Ly hat. Because commutator A hat to B hat is equal to minus commutator B hat A hat. These are various commuting property relationship of angular momentum operators. Thus, it is possible to find out the square of the angular momentum and any one component of angular momentum simultaneously and precisely. So, their operators commute each other. However, it is impossible to find out any two components of angular momentum simultaneously and precisely. So, the component operators of any two component operators of angular momentum will not commute each other. That all about the commuting relationship of angular momentum operators. Now, we are moving on to the final portion of the discussion, that are important properties of Hermitian operators and their proof. First one, all the eigenvalues of a Hermitian operator are real, and the second one, two eigenfunctions of a Hermitian operator with different eigenvalues are orthogonal to each other. Now we have to prove these two properties of Hermitian operator. I am going to the proof of the first statement, that is all eigenvalues of a Hermitian operator are real. For this, we have to proceed in a systematic way. First of all, consider an operator A hat. Consider an operator A hat. A hat operates on a function psi, and the result is, let the result is the psi back multiplied with a constant lambda. This is the eigenvalue equation. Here, psi is the eigenfunction of operator A hat. That means A hat operates on psi to get psi back multiplied with a constant lambda. Here lambda is the eigenvalue. And we are discussing properties of the Hermitian operator. And we have to prove that the eigenvalues of a Hermitian operator are real. Real means there is no imaginary number. That means ultimately we have to prove lambda equal to lambda star. Lambda is the eigenvalue. Lambda star is the complex conjugate. If lambda equal to lambda star, it is clear that there is no imaginary term in lambda. That is we are going to prove. For this I am beginning this from this equation. I mark it as equation number 1. A hat psi is equal to lambda into psi. Now left multiplying equation 1 with the psi star. Left multiplying equation 1 with the psi star. So we are getting psi star A hat psi equal to lambda psi star psi and integrate over space. Left multiplying with the psi star and integrate over space. So integral, limit is from minus infinity to plus infinity. Here I am putting a d2. Here also lambda can be taken outside the sign. Integral psi star psi d2. So what I made here is left multiplying equation 1 with the psi star and integrate over space. That is I got integral psi star I had to psi d2 equal to lambda into psi star psi d2. I mark it as equation number 2. Now take the complex conjugate of equation 1. That means replace every terms with their star. Starred terms. That is complex conjugate. Thus the complex conjugate of each term, after taking complex conjugate of each term in equation 1, I got the expression A hat star psi star equal to lambda star psi star. I mark it as equation number 2. Now left multiplying with the psi and integrate over space. Left multiplying with the psi and integrate over space. So I got psi A hat star psi star equal to lambda star can be taken outside the sign or can be taken in front. Psi star and perform integration. So integral psi A hat star psi star over space, integrate over space. This is psi star d2. Or simply integral psi A hat star psi star can be represented as A hat psi the whole star d2 is equal to lambda star integral psi star d2 can also be taken as 4 into 3 is equal to 3 into 4 like that. Psi star psi d2. I mark it as equation number this is equation number 3 and this is equation number 4. On comparing equation number 2 with the equation number 4. That is the further step. Just look on to the left hand side of these two equations. The left hand side of equation 2 is integral psi star A hat psi d2. Left hand side of equation 4 is integral psi A hat psi the whole star d2. We already learned about the Hermitian property. An operator A hat is said to be Hermitian if integral psi I star A hat psi j d2 equal to integral psi j A hat psi I the whole star d2. In analogous with that, if I replace the subscript I and j, psi star A hat psi d2 is equal to psi A hat psi star d2. That implies the LHS of equation 2 and LHS of equation 4 are same. These two terms are same. That means we can equate right hand side. Now take the right hand side of equation 2 and 4. Left hand side is lambda into integral psi star psi d tau, and RHS equal to lambda star into integral psi star psi d tau. These two terms will vanish such that we got the final relation lambda is equal to lambda star. Lambda is equal to lambda star means one quantity same as its complex conjugate. This is happened if and only if there will be no imaginary number. That means the eigenvalue lambda is real. That means all the eigenvalues of a Hermitian operator are real. Now we are going to discuss the second property of Hermitian operator. The second property is two eigenfunctions with the different eigenvalue of a Hermitian operator are mutually orthogonal. We are going to prove this statement. First of all, let us have a Hermitian operator A hat and consider two of its eigenfunctions. Let the eigenfunctions are psi1 and psi2 with the different eigenvalues lambda 1 and lambda 2. Based on this, I can construct two equations. That is A hat psi1 equal to lambda 1 psi1. I mark it as equation 1. Also, A hat psi2 is equal to lambda 2 psi2. I mark it as equation number 2. Now, to prove this, take equation 1 first and take complex conjugate of each and every terms in equation 1 such that I got A hat star psi1 star equal to lambda 1 star psi1 star. I mark it as equation number 3. Left multiplying with the psi2 and integrate over space in equation 3. That is, left multiply equation 3 with the psi2 and integrate over space. Thus, on left multiplication, psi2 A hat star psi1 star d tau integral over space equal to lambda 1 star integral psi2 psi1 star d tau. I mark it as equation number 4. Similarly, we have to take equation 2. In equation 2, left multiply with the psi1 star and integrate over space. Take equation 2, left multiply with psi1 star and integrate over space. On left multiplication with the psi1 star, we get psi1 star A hat psi2 on integration put d tau is equal to lambda 2 integral left multiply with the psi1 star psi1 star psi2 d tau. I mark it as equation number 5. Now we can take LHS of equation 4 and equation 5. LHS of left hand sides of equation 4 and equation 5. LHS of equation 4 is this, that is integral psi2 A hat psi1 the whole star, I can put it as whole star d tau, and LHS of equation 5 is integral psi1 star A hat psi2 d tau. if psi 1 and psi 2 are two Hermitian operator, psi 1 star a hat psi 2 d tau will be equal to psi 2 a hat psi 1 the whole star d tau. So, as per Hermitian property of psi 1 and psi 2, we can equate these two. That means right hand side of equation 4 and 5 would be the same since LHS are the same. That is, we can write psi lambda 1 star integral psi 2 psi 1 star d tau, that is right hand side of equation 4 equal to right hand side of equation 5, integral psi 1 star psi 2 d tau, psi 1 star psi 2 d tau. And it is clear that the eigenvalues of Hermitian operator are always real. Therefore, lambda 1 star is same as lambda 1, such that this term can also be moved on to the left hand side to get a zero relation. Psi 2 psi 1 star d tau same as psi 1 star psi 2 d tau. So, I can rearrange these terms. Lambda 1 minus lambda 2 into integral psi 1 star psi 2 d tau, that is equal to 0. See, this is a product of two terms. Lambda 1 minus lambda 2 is the first term and integral psi 1 star psi 2 d tau is the second term. It is clear that in order to get right hand side equal to 0, either one of these terms should be 0. But it is clear that lambda 1 is different from lambda 2. So, lambda 1 minus lambda 2 not equal to 0. That ultimately leads to the result integral psi 1 star psi 2 d tau equal to 0. This is clearly the condition for orthogonality. If two functions psi 1 and psi 2 are orthogonal, then integral psi 1 star psi 2 d tau will be equal to 0. Thus, we proved that two eigenfunctions with different eigenvalues of a Hermitian operator are mutually orthogonal. Thus, we have discussed the complete properties of the Hermitian operator. That's all about this module. Thank you.